So the reason why I'm here in Singapore this time is tomorrow I'm going to be speaking at the Supercomputing Frontiers conference, and I promised that I would advertise it. So there's the advertisement. It's tomorrow through the 18th over in Biopolis, and you can just Google Supercomputing Frontiers for the details of what time it starts and so forth, the registration procedures. What's great about Julia is that I'm kind of equally at home talking at a supercomputing conference where people are doing sort of more traditional scientific computing. I'm happy to talk about Julia to data science group, people doing big data and machine learning, and the sorts of things that you guys are doing, and it kind of works just the same. So the plan here is I'll talk maybe about 30 minutes, and then Ro Shao here will talk maybe about 30 minutes or so. I'll give a bit of an introductory talk. Ro will dive into some details, I think. So, but I've got the sense that how many people have actually used Julia? Let me just find out. How many have typed 1 + 1 in Julia? Okay, so I think an introductory talk is just right. So, interestingly enough, there's some serious thought leadership about Julia in Singapore. I just found out that Mark might have been here today, but I guess he got busy, so I'll see him tomorrow. But he's been very much active in trying to get Julia on every desktop, every laptop, going as far as being towards the exascale, all in Singapore. So Singapore would be kind of a great place to be able to do that sort of thing. So for all of those who didn't raise their hand, Julia's coming down the pike here in Singapore, so get ready for it. Okay, so first of all, why Julia? Well, this slide here, I need to get it out of the way. It's what everybody wants to hear first. But actually, it's not the most important thing about Julia, not in my opinion. So, Julia is fast. Julia is really, really fast, and people seem to like speed. So here are some benchmarks. There are these 6 different benchmarks in a whole bunch of different languages. And the way you read this chart is, this is done as a comparison to C code. So, 1, which is indicated as 10 to the 0, is on par with C. Actually, if you're below that, you're even faster than C. And then there's, 10 times C, 100 times C, 1,000. And, Julia's fits right in this narrow little box. But I've got to tell you that I remember I've been giving a whole lot of talks about Julia. And maybe it was about a year ago, it was over at MIT, where I'm a professor. And I heard some folks in the back saying, oh, this Alan guy, he's always talking about Julia. There's all this hype about speed. It's like, it's just hype though. Don't. So what I tell people is, you know what? Forget about these benchmarks. These benchmarks don't mean anything to you. Go ahead and just pick up Julia, write your own code, and measure the speed for yourself. And so people started to do that, and then they, you know what? This isn't hype at all. Julia really is indeed fast. And now there are some industry benchmarks. People are really getting the idea that Julia is fast. By the way, by all means, feel free to ask questions at any time. It's, that we Americans, we like to be interrupted. If you don't interrupt us, we feel offended. So, yeah?
Where would Cython fall on this chart?
So Cython is, what is Cython? Is it C?
If you'd written all of it in C, then it would fall right on the line 1.
Right. I mean, that's the right question. And in fact, that actually kind of brings up a point, which is, what is a language? What are these things, right? The thing that makes Julia really wonderful is that, by and large, Julia is Julia all the way down. It's not an interface to some other language. I mean, there are other languages that we plug in, and there's LLVM at the bottom, but basically Julia is Julia all the way down. And so that we're measuring Julia in a way. We're not measuring a layer on top of something else. Okay, but thank you for interrupting. Now I'm already a little happier. All of you have to do this too.
Happy to help out.
Perfect. So I've got a couple of slides that kind of show some of the industries where Julia's out there just for fun. If you haven't seen some of the places, one of the things that we're excited about is the fact that Julia is being used as a specification language for airplanes not banging into each other, and we're all in favor of airplanes staying physically separated while they're up in the sky. What made Julia really kind of wonderful in this area is that instead of simply like writing down a spec on a piece of paper and then coding it up, the actual process of writing it down was writing code, which people could read, but also was at the same time a program. And so, of course, you eliminate all that middle stuff that leads to confusion and mistakes. And went directly into the code. So that's one place where it shows up. And in fact, this kind of reminds me that more and more people are using Julia in a way where safety is a concern, or where sort of verifying what you've done is a concern. So you probably all heard about that Volkswagen fiasco that happened, where you couldn't really know what the code was doing. And Julia is great because it's easy to read the code. So not only is it open source, people like open source because it's possible to read it, but people like code that's easy to read because then you really will read it, right? There's that extra level. And Julia does that. I just like this picture, and that's why I'm showing it to you, but Voxel 8 has Julia, there's a 3D printer right here. This is a quadcopter, and Julia's actually driving the code that does this. Here's another one for healthcare, and just to mention that Julia's kind of being taught now. The pace is accelerating. This is the poster for my own course, but there's also the ones that we know about. Here's a list of some of the courses. I think this is already a little old, but Julia's being used. Apparently, we were told by a professor at Stanford that now Julia. I don't know the detail, but in some widely popular course, Julia now is outpacing MATLAB. So Julia is happening. It's out there. It's happening. And I guess I just saw a newspaper article today where people were saying that people with skills like Julia's skills are starting to make more money or something. I don't know. There's some like so, well, think about it. If you could be more productive, right? You can impress your boss, and then you get raises, you get promotions. So this is actually happening at the grassroots level at a lot of companies. All right. So what I've said about Julia, let me sort of go back to my title slide. Fast, flexible, and fun, right? So we've covered the fast part. Let's go to the flexible and fun now.
Sir, you mentioned Julia is fast, but what makes it fast compared to other languages?
Oh, I mean, that's a whole other talk. What makes Julia fast is so multiple dispatch. What I tell people is if you want the two words, like you want to sound really smart, next time you go to one of these meetups and somebody asks you why Julia's fast, you don't have to understand it. Just say multiple dispatch.
And if they ask what it means?
Sorry?
If they ask what it means, how do I explain it?
They'll tell them you have to take 5 years of computer science. No, I'll do better than that. So Julia is fast. Why is an airplane fast? Before I tell you, why is an airplane fast? Somebody tell me why an airplane is fast. Because it has a fast engine? Because it flies in the sky? Why is an airplane fast?
What kind of airplane?
What kind of airplane?
But I mean, it's
why is a jet plane fast?
Airplanes versus programming language, same thing. I mean,
Why is an airplane faster than a car?
Oh.
It's got
Bigger engine.
It's got a bigger engine. Yeah, maybe. It's kind of so Julia's fast because in a way before I even how about another one? Why are certain algorithms fast? Like why are certain sorting algorithms faster than others?
They take less operations.
They do fewer operations, right? So they avoid the muck that the slower ones do, right? They avoid the unnecessary part of the computation, right? They somehow get to the heart of what needs to be done, right? They're very efficient about doing what needs to be done. So when Julia gets compiled, it's through the various. Again, this isn't this talk, so I'm trying to sort of take a whole talk and put it in a few sentences. Julia's language constructs allow the user to help the computer to basically have everything end up fast. Okay, so that's kind of the quick summary of it all. All right, and that's not a fully adequate answer, and I recognize that, but again, that's a subject for another. By the way, I gave that talk 2 months ago at NUS, Why is Julia Fast? But it was a small audience.
Can you pull up the SAM news article with the code? Or?
Not right now, but I could, maybe later. I really should do that? The SIAM news article? Let's get to it later. Let's get to it later. I don't want to go down the road of why Julia's fast completely right now. We could, but anyway. All right, I was going to go past fast and get to flexible and then fun. See, if I spend all my time on fast, I'll never get to flexible and fun. So the next part of the talk is about flexible. So I kind of like this. So I like linear algebra. Linear algebra is great. I love matrices. Matrices show up in the kind of scientific computing like the audience for tomorrow, and matrices show up in the kind of big machine learning, big data. Matrices are somehow everywhere. So I just love matrices. I love linear algebra, and I found this kind of sequence of for loops in some slides by Jim Demel at UC Berkeley. So probably a lot of you know that the kinds of matrix computations that you find in all the languages, MATLAB, R, Python, whatever, they're by and large all LA packed under the hood, right? They're all that linear algebra package, right? It's not. There's really like no SVD in R or MATLAB, right? It's simply a call to the SVD in LA pack, right? So Jim Demel is one of the forces behind LAPACK for many years. He and Jack DeGara, and he was talking about sort of the difficulty of being in the position that he's in. That he has to worry about all the linear algebra problems, from solving linear systems to doing singular value decompositions to doing eigenvalues. He has to worry about all the linear algebra problems, and he has to worry about different kinds of matrix structures, dense matrices, sparse matrices, big matrices, little matrices. He has to worry about all these things. And he has to worry about for all data types. So for him, that usually just means 32-bit floats and 64-bit floats and 32-bit complexes and 64-bit complexes, that kind of stuff. For all architectures and networks, for all programming interfaces, get the best algorithm. I think he was just trying to show off just how hard this task really is, with the complexity of doing it. But this sort of stuff doesn't really scare the Julia folks. This explosion of complexity could really be anyone's big problem. And so, forget about linear algebra. Not everybody loves linear algebra as much as I do. I think that's true. Maybe that's true. But everybody here is interested in today's audience, it's the big data problem. Tomorrow it might be the exascale problem. And what replaces matrix structures is whatever computational representation you might have. And these days, it's not just instant floats. It could be big nums, symbolic computing, interval arithmetic. The inventor of unums, if you've heard about that, is right here in Singapore, and we've been getting involved with that. This is sort of a new way to get higher accuracy answers. So there are all these different kinds of data types out there, and you want your code to work. Okay, and of course, there's the architectures, which everybody worries about. You have to rewrite your code for all these different kinds. You want to work on a GPU. Do you have to start all over again? You want to go to an exascale computer, like there's going to be the big deal tomorrow. Do you write your code all over again? The idea is, by and large, you don't want to do that. The real truth is, what you want to do is you want to have certain pieces that are specialized to your architecture. You want to have those available as always. But your big pieces of code you want to reuse and have it work everywhere, right? And one of the things that Julia lets you do is kind of balance those. It's a bit of a balancing act. What do you write? See, I've seen this over and over again. When a new architecture comes along, someone might take an old code, copy it into the directory, and then start modifying it like crazy. They don't use the same code. They might just use it as a basis. But in the end, it's a new, different code. Julia makes it easy to keep the pieces that deserve to be kept. And so that's sort of a big deal about Julia. And so, of course, not only do you want the best algorithms, but you want the best software. So I've got a couple of case studies. One is Andreas Novak, who's actually working at MIT. He's been building a cross-cutting library that he wants to work on Intel Xeon Phi. He wants it to work on the GPUs available through ArrayFire. He wants it to work on pure native Julia parallel arrays. There's the elemental library out of Stanford. He wants all of these things to work. And he sent me an email and told me that he's really happy because he gets complete code reuse, complete function overloading. By and large, if you look at the code for all of these things, it's not separate. It's not 4 separate pieces of code. It's one code that, of course, might be calling separate things under the hood, but it's really one code base that he has to maintain. And I'm not a C++ person, so I'm kind of the wrong person to show you this. If you ask me any questions, I probably won't know the answer. But people would say, can't this be done in other languages? And basically the answer is, to some extent you can, but Julia is really the best place, in his opinion, he's happy working with an interactive language. You don't have to compile the entire power set of possibilities, still get the speed of like a C or a C++. So, that's the real message here is flexible code that basically allows you to switch architectures, switch data types, and still the thing is powerful enough to be useful. Okay, and the next part is Julia's fun, but before I get there, I thought I would give you, I haven't really shown you any Julia code yet, and I kind of think it would be nice to take you through a little bit of a notebook, especially one that I think would appeal to a data science kind of audience. So I've got this notebook right here, and I'd like to show it to you. So this is an ECG model. Let me give you a little background to this. I don't know if this is too small, but let's full screen this. Okay, and do something like that. Is this going to work? So let me tell you the story of this notebook. It's still getting bigger, maybe too big now. So on the same floor at MIT where we have got sort of Julia's a worldwide effort, but we kind of have our own group right in the first floor of the computer science building at MIT. And right on that very same floor is my colleague Peter Solowitz, who's devoted his entire career to computer science in the medical area. So he's been very big about bringing computer science principles into medicine, and medicine, of course, is a place where there could be lots and lots of data. And he got all excited about Julia and kind of brought us all in, and shared with us this data set. Actually, we have a whole bunch of data sets from him, but one that was pretty cool were these electrocardiograms that. So basically, let me see if I could show you these pictures. You've all seen this sort of heartbeat data. Something that might look a little bit like this. So he's got the data. He's got all of these electrocardiograms, and he knows sometimes they're labeled healthy. Sometimes he knows that somebody has a certain kind of disease. In many cases, these are people who passed away, and they know exactly the lifespan and what age. All sorts of demographic information. He's got tons and tons of stuff. And what he told us was the way this data is traditionally used is a doctor has some hypothesis of some sort, that a waveform of a certain kind is associated with something. I don't know. I'm not a doctor, and to me this is just data. Don't ask me anything medical. But what does happen is doctors have some hypothesis, and so they'll go in and they'll try to see if they could learn whether their hypothesis is true or false based on the data. What they don't do, or at least what they haven't done traditionally, is simply take the data as data and have a computer look for something interesting that maybe a human would never find. That, to me, I feel the difference between the sort of old kind of expert systems like language translators, where you try to find out what an expert knows and then try to code it, and we all know that doesn't work very well. Or you could simply just learn from the data itself. Translating, if you translate Chinese to English or something, if you just have lots and lots of examples, we all know that machine learning works way better than trying to take a human and capture the system. Well, in this medical world, nobody's doing that second kind of stuff, at least according to my colleague. So we just thought we'd kind of start. I mean, we're not going to be the ones who'll get anywhere. But as far as a Julia demo, it makes for a pretty good demo. So what we did is we found a model for these ECGs. And again, I'm not going to take you all through it, but here, let me just make this just the right size for the screen. What I really want you to see, I certainly don't want you to learn the model, but what I want you to see is that there's a little bit of math, some square roots and sines and arctangents, basic kinds of math. I mean, this probably looks just like the formulas that you would probably find on the paper. In fact, I think it looks exactly like it, because all the Greek letters, 2 pi and everything like that is easy to type.
Prof, for the IDE of your Julia, is there a special keyboard, or you have to insert this?
Oh, good question. So if you want, here, let's show you how you get these cool letters. All right, so if you want pi, actually let me insert a cell here. So that's a good question. So suppose you want pi, you type \pi tab, and you hit return, and there you go. So that's how you do it. In fact, I'll tell you a little secret. Every once in a while, I want some Greek letters in my emails. What I do is I open up Julia, and I just tab, and then I copy and paste it, and I could just copy and paste it, and and I put it in my emails. So
Greek websites.
Oh, am I getting Greek websites, or am I getting math websites? Scholarly articles on alpha, beta, gamma. Oh, this one looks like a really good one. The entire Greek alphabet. Greek. There we go. That makes sense. Okay, so that's all.
You want to do the subscripts and the superscripts?
Oh, let's go for it. Let's start with the square root. There's a square root of 2. You can do subscripts, no problem. And so, if you can copy and paste this stuff, I could square, So basically, all of these become some people think that as cool as Julia is, this is even the coolest part. Yeah.
Is the syntax the same as the LaTeX?
Yes, it's for starters, yeah. Basically, you recognize it as LaTeX or LaTeX or however or LaTeX or whatever you pronounce it. But
this also works in Emacs. So if you use the Julia mode in Emacs, you can, as you program, just do exactly the same thing.
Yeah, I definitely find myself using Sigma a lot. I don't know why, but I do. So no special keyboards. I don't know how many of you are old enough to remember the old APL days. There was that programming language from a long time ago. It did have a special keyboard, and there are a lot of people who conjecture that was part of its reason for its demise. Yeah, no special keyboard. You just type kind of LaTeX-like things. All right, back to our story. There was some paper that had a model for doing this sort of ECG kind of waveforms that you basically set up some formulas, solve an ODE, and boom, you plot heartbeats. So here's sort of a kind of heartbeat that you might get from doing this. And so this is a model. This is not data at the moment. We have data as well. But this is a model for heartbeats. And in fact, in a way, this is what you want to be able to do. You want to have data, you'd like to have a model, and then you'd like to be able to compare them, right? That's to me what data science should be. But that's not what they were doing. So we just made up a story of what we thought they ought to be doing. Not that we know anything about, we're not presumptuous that they're doing anything wrong, but this was just in my head what one ought to do. So here's the model, and one of the nice things is you get to play with the model. So you could change, there's a whole bunch of parameters. I gather these PQ, RS, and T's refer to I think doctors look at this and they say, oh, R is 2.7. Somehow it's describing the waveform in some way. But in any event, if you want to get to know this sort of thing, you can, watch the dancing heartbeats. It's kind of fun. So, but again, if you're a data scientist, you want to be able to build tools like this. Like, you're trying to model a situation, and you want to be able to get to play with your model and get to know what you're looking for, right? These are the tools that, again, I think a data scientist wants to have, right? This sort of thing. And I guess I'm inspired by the fact that, I mentioned I've been to Singapore many times. I've got some teenage boys, and I've been taking them to Singapore since they were little, and we would go over to the science museum. You guys have a great science museum here in Singapore. And what's so wonderful about it is there's always knobs and buttons and things you can push, right? And what I realize is not only do kids love that, but adults like it too, right? If you don't have knobs that you can do, forget it. Like, don't use that language, right? I don't know. You got to have knobs. Don't go to the museum if it doesn't have sliders. So here's a slightly more intense model with more parameters. I think I have to make the screen smaller just to. I can get it. That's probably small enough. So here again, there are all these parameters. I have no idea what they do. Some of them don't do anything. This one, there's this one. Anyway, you can get the notebook and play with it, but some of them are subtle. Some of them are more. But in any event, you can get to understand what these things are, and you can match things up. And again, you've got your heartbeat model. You can fiddle with it. So. Zhihao is great. He put together, many versions of this. But there's the model. I'm not. My job here is not to do that. The next step is to take the data. Sorry. The next step is to do what a data scientist would do, is to try to get the principal components, right? So the SVD of this sort of thing. And so we've got an SVD kind of analysis. We've got if you see, we've got like an SVD explorer. So what we do is we take this heartbeat data and we just run it through an SVD. Again, this is like what a data scientist should do. So so we break up the data into these are the singular values. If you don't know about principal components or singular values, this first one is supposed to have like the most information, right? Then the next one should have some corrections, so to speak, right? And then it gets smaller and smaller corrections, right? And then the singular vectors, there's a left one and a right one, correspond to something about a feature. Okay, and again, one can play with this. I don't know what it means. Maybe nobody does, but you can play with it, and you can get to know what it means. You can get a feeling for these. So I'm not sure which one of these is, but one of these actually has the real hospital data. The other is the model. And again, you can look around and try to match these things up. All right, so, I could show you more of this stuff. Again, I don't know what any of this stuff means. But the big picture I get. The big picture really is, there's a lot of, we've got tons of this stuff here. But looking for all kinds of anomalies, and I don't even know what we're looking at here. But the big picture, I think, is very, very clear. That you want to have a system that you can interact with, you can build up a model, and it's not really complicated to do it. And you can actually take the data and analyze it and try to, look and see what you might find. The computer can look, you as a human can look together, whatever makes sense, right? And so to me, that's the data story. Okay. All right. So that's some. And hopefully, as I did this, I know I flashed it by very fast, but at least you got to see what Julia code looks like. And I hope you realize that Julia is really very, very quick to learn. People usually learn it very, very fast. It's similar enough to other data science languages that if you want to pick it up, you almost know it. There's always the idiosyncrasies that'll drive you crazy, but that's usually for 3 days, and then you're happy again. Right, and so you got to allow those for those 3 days. Okay, so let's go back to Julia's fun. So as I mentioned, I'm here for a parallel computing conference tomorrow, and I gave this class on high performance computing at MIT last semester, and in this course, I never give finals because then I have to grade them. That's no fun. That's my job. I don't want to do that. So what I invite the students to do is to do projects. And I give suggestions, but basically the students pick their own projects. There was one student who works in robotics, and he wanted to work with these very fun robots, these Lego Mindstorms. So apparently, so the student's name was Robin Dietz, and apparently he, long before he became a graduate student working with real professional robots, he was working with these Lego robots ever since he was little. Yeah, so anybody here play with these things a little bit? Have some fun? More people than played with Julia, so we've got to kind of round it all out. So when I told the student that this would be a great project and I would allow him to do it, he didn't quite believe it. And in fact, he told me at the end of the semester after his grades that he was kind of shocked that I would let him play with toys and he could still get credit for an MIT course. He was so happy. But I think this was one of the coolest projects. This is a parallel project. I'll show you why in a minute. But it also gets covered in there's the internet of what's the word that always keeps coming up? Well, maybe, but we decided to call it this. So if you have lots and lots of robots, out there and they're talking and connected, then it's the internet of toys. By the way, I showed you this medical data and I showed you Julia running. But imagine that if you have a language that's flexible enough to be able to get heartbeat data in software running on your laptop, but if it could also run, suppose you've got some sort of heart monitor strapped around your chest, monitoring for you and running the very same code. Do you see the power of that? That instead of having some engineer go and rewrite the code for the heartbeat data on your laptop, if you could run the very, very same code on your laptop, on a machine on your chest, on some other big supercomputer, there's power in that. I mean, you can say, oh, what's the big deal? You can rewrite code. It is a big deal. It is a big deal. To be able to see the same code and read the same language everywhere it runs, it is a big deal. All right, so where was I? The Internet of Toys. So like I said, Robin was playing with these things ever since he was a kid. He was showing me how he started out with this, and then he had that one, and now, so with all the versions of all this. And what he decided to do for the class project, see, I love this because this is what parallelism. When I've been in parallel computing for a while, and I have this climate models and these big fluid flow computations and big PDEs. But this is also parallel computing once you have more than one robot. And to me, this is sort of the modern parallel computing. So this was real fun because he actually brought them in and in a room like this, and he put it on the floor, and everybody got to watch the robot. It was pretty cool. So here's a robot sort of moving around. This picture was taken in his lab. It would drive around. So here, this green thing was the path of the robot itself, and it had some ultrasound sensor that tried to sort of have a good feel for where the walls were. So it doesn't know where the walls are. So these red dots are the best it can get at sort of seeing the walls, and it would build a local map of what it observes. And he kind of showed us all the code. And basically, there was some code to construct the robot, sort of in the software piece of the robot, and then run the mapping that I showed you in the picture. And then he said, when it came time to work on more than one robot, all he did was just set up the different host names, the IP addresses of the computers. They each had little networks on them, and then he just basically put in the @parallel, and boom, he had a parallel robot application. So he showed this pictures. He had made a little movie. The movie didn't. I think it's one of those you had to be there. Like if you were right here and watched them go, it was pretty fun, making all the noises, all the whirring noises. You have to imagine it, but it was moving around and doing this sort of thing, and I just couldn't help but envision, Star Wars, the Clone Wars, that's massive parallelism to me, right? The large number of robots that you'd have over there. All right, so Julia's fun. I've got a couple of more slides, and then I'm going to pass it over to Viral here. So just another sort of set of slides I'm kind of stealing from some work that was done over at Intel by Kiran Pamnani and Rajan Anantharaman. who's now, by the way, working for Julia Computing. But he did this work when he was at Intel. And I just have a couple of slides that I thought that might interest you. So these are some stock correlation computations, and some of these are, MATLAB vectorized, devectorized in various ways, and on a GPU, called from MATLAB. And here's Julia's threading, and we're kind of excited that pure Julia, just simply threaded, is kind of reaching that very, very same stage. And so you can sort of see the speed ups. Again, I'm here for a parallel computing conference, so I kind of have to show this sort of parallels in slides. So you can sort of see the things. And so parallel Julia is working just as well as maybe here's the point of this slide and some of these other slides. I grew up believing that if you had a dynamic language, then you had to get your speed from some other language. So I always believed, for example, that if you wanted to get a matrix library, you had to have that in another language, and then of course you could put some fluff on top, like scripting stuff on top. And over again I'm hearing, no, it's not true. It's kind of like blows my mind, that I feel like it's violating the speed of light or something. But no, you could actually write code in Julia, and you can replace, if you want to, you could take every library that's out there, LAPACK, FFT, whatever library you have, you could, you have to do the work, and some people would say, why bother, we already have these libraries. But the point is you can do these things in Julia, and you'll get the speeds of these libraries. You really will, or the speed of the architecture in this case, and it really, really does work. Okay, so this is really for tomorrow. I think I'll pass it right now. Just people are saying that exascale is going to be a problem, and Julia, maybe it's worth saying this, that usually one thinks of domain-specific languages, like there's a data science language, and maybe that's over here, and there's the scientific computing language, that's like over at Biopolis or something, right? They're like physically separated. And the Julia world doesn't feel that way. The Julia world feels that if you've got the right kind of language, in the end, it's all kind of like, math and computational constructions. It's not like, there shouldn't be a data science language and a PDE language. And maybe there are people who specialize in one and hate the other thing. But the language shouldn't distinguish those. So this is my conclusion, but again, Verl's going to follow up on some of the things that I said. But fast, flexible, and fun, and it could be just as valuable for big data, scientific computing, learning, and exascale, all in one. Why not? Because they're all based on the same computation and mathematics. And so thanks everyone.